Okay, let's get started. It's great to see so many of you here in person. It's a Caltech tradition that every year we invite an eminent scientist to give the Lauritsen Memorial Lecture. The Lauritsen Lecture is named in honor of two Caltech professors, Charles C. Lauritsen and Thomas Lauritsen, who were father and son. They were born in Denmark, but when Tommy Lauritsen was just a baby, C.C. Lauritsen emigrated to the U.S., and he worked as a radio engineer for some years until he heard a lecture by Robert Millikan, which inspired him to enroll as a PhD student at Caltech. And it was the work of C.C. Lauritsen under Millikan's supervision that attracted the attention of W.K. Kellogg, who had invented cornflakes and had other interests besides breakfast cereal, and that led to the erection of the Kellogg Radiation Laboratory in 1932, a historic Caltech building which still stands not far from where we are now. And Tommy Lauritsen attended Caltech as both an undergrad and a graduate student, and then after the war joined his father on the Caltech faculty. And in the 40s, 50s, and 60s, the Lauritsens, Willie Fowler, and other colleagues established the Kellogg Radiation Laboratory as a world-leading center for nuclear physics and nuclear astrophysics. I forgot to mention, what was it that C.C. Lauritsen was doing that got Kellogg excited? He was studying the use of X-rays to treat cancer. And the Lauritsens are remembered as not just outstanding researchers, but also tireless service to the Caltech community and the broader scientific community. So we're very excited this year to have as our Lauritsen lecturer, Peter Zoller. Like the Lauritsens, Peter found a place he liked and stuck to it. He got his doctorate in 1977 at the University of Innsbruck, and soon after joined the faculty. And aside from a few years at Gila at the University of Colorado, he's been there since then for many years now as the leader of the theory group at the Institute for Quantum Optics and Quantum Information of the Austrian Academy of Sciences in Innsbruck. And I think I can say without exaggerating that Peter is one of the world's great theoretical physicists. He works in the area of atomic molecular optical physics, but saying that doesn't really do justice to the scope and impact of his contributions. Actually, AMO physics has undergone a very profound transformation in the last few decades, and to a large extent that's because of two developments. One, the realization that we can use AMO systems like trapped ions for coherent quantum information processing, and the other that we can use AMO systems like ultra-cold atoms to study quantum many-body physics in a regime that's never been experimentally accessible by other means. And those two rich themes of science really sprang from Peter's contributions with his collaborators over 20 years ago. And he's remained at the forefront of those fields, as we will be witnessing today. So I'm really highly honored to introduce a scientist for whom I have the highest admiration, Peter Zoller, to tell us about programming atomic simulators with atoms and ions. Peter.
Okay, thank you. So let me first of all thank John for introducing me here and also for inviting me to spend the whole week here. That has been very exciting. I have to say, I've been grounded in my home office for more than 2 years. This is the first time that I see a real audience in front of me, and I'm feeling like a young graduate student, that's a little bit nervous because, it's sort of the encounter with the unknown. But I'm really excited to be here. I had a fantastic week talking about physics. What I would like to do here today is to talk about, programmable or programming quantum simulators with atoms and ions. And John already mentioned that my own background is more in quantum optics, theoretical quantum optics, atomic physics. But I would say that, 25 years ago, my life and our life in atomic physics really changed. That quantum information entered. We knew how to engineer, quantum many-body systems, either to build quantum computers or maybe to build quantum simulators and all of that. There was a whole new exciting possibilities coming up. And I would say that quantum optics and atomic physics has played, I guess, a major role in developing some of these ideas and systems. Particularly also leading, I would say, together, with some of the other condensed matter systems, the experimental effort that we had in this direction. So I just put down here, a few examples. We worked on trapped ions with Ignacio Chirac, optical lattice, Harvard model, and all of that. The Rydberg atoms with Misha Lukin, we came up with the idea of having a Rydberg blockade mechanism. Polar molecules were on our list, and of course the real quantum optics over here. And in retrospect, I mean, these ideas here would classify what John would call atomic NISQ devices, in the sense that we're building quantum systems. They're not error corrected, so in this sense they're noisy. But the great thing that you will now see in the following, that's the reason for talking about this, that they have sort of two properties over here. They're scalable, number one, they're relatively large particle numbers, and they have some sort of programmability, not universal like a quantum computer would be, but they have some amount of programmability. But I would say that the combination of these two things allows us to do today in the labs, a lot of interesting stuff. And of course, when I see Manuel Endless here, I mean, he's just doing the same kind of physics, of course, also here at Caltech. What I would like to do in my talk, and this is sort of appropriate maybe to a colloquium, to give you a little tour about things where we as theorists sort of, not like in the old days, we came up with some proposal and it took years maybe to realize that. Today, I think we have the exciting possibilities and opportunities that when we have new theoretical ideas, we can very often go directly to the experimental and say, hey, can you try to do that? And of course, you have to convince the experimentalist that it's, number one, exciting what you propose, and number two, that it's feasible. But very often, feasibility is there, and the excitement front you have to work on a little bit, of course. And so in this sense, I would like to talk today about our collaboration with Rainer Platz's group over here. We trap ions where we take ideas that we have and we right away take them into the lab and we can try them out. And I think that this is sort of a change in paradigm for me, because after all these years when we thought about some of these ideas, we are finally at the point where these things are coming back to us. We dreamed of programmable quantum devices, and now they're back to us in small scale and so on, but we can play with them. So I feel that this is very exciting. Let me give you a little bit of background with all of these things before I start the real stuff here. As I said, 25 years ago, we thought about quantum computing with Ignacio Chirac. These ideas of having trapped ions. This is a string of ions. You can, each of these ions can represent a single qubit, spin up and spin down. And this, you can manipulate that with laser light and so on. At the end, coming up with ideas where we're using, for example, phonon modes here to create different kind of entangling gates and so on. The main emphasis on the left-hand side was really sort of, demonstrating quantum algorithms. On the right-hand side, we have quantum many-body physics, a sort of more condensed matter-type physics, where you might create things like a Harvard model. But really, the questions on the left and right-hand side were rather different in terms of culture, what one was asking. Let me emphasize that on the left-hand side, of course, we have a fully programmable universal device, but usually a small number of qubits. Eventually, of course, we need error correction to make it meaningful. On the right-hand side, we have these analog simulators that are scalable, but they only realize a very particular class, small class of Hamiltonians. But they do that with relatively high fidelity. But of course, during recent years, a lot of control has been added to these systems. One of them is this observation of single atoms, like with the quantum gas microscope. But at the end, this has led to something that we call now programmable analog quantum simulator, which is really the topic of what we would like to talk about in the context of the ions. There, of course, on the ion side, we might have a string of ions. And as an analog simulator, they realize, a certain model, like this transverse Ising model that I'm writing down over here with a long-range interaction. But you can also add to the whole story here single-site addressability. So you have a combination that we know how to entangle with this particular Hamiltonian. This is one control, but also single-site addressing over here, and also corresponding readout. And completely in parallel, of course, with the Rydberg tweezer arrays. The exciting thing on the Rydberg tweezer side is that they really scale sort of more to two-dimensional systems, even three-dimensional systems, and so on. And these are kind of the list devices that I want to take now as the basis of my talk now here in the following. Let me also just mention that, on the Innsbruck side, this is the Innsbruck campus, there's the university, this is the academy over here, this is our companies over here. I'm sort of in the second row participating in one that tries to build a quantum computer based on trapped ions. If you take these two buildings, the experiments by Rainer Blatt and Thomas Mons are sort of on one hand this quantum computer that typically, you've used them up to about 26 qubits. I will show you afterwards one example. Or then a programmable quantum simulator, the other building over here, of the Equoquia labs downstairs, which in the meantime, that's very exciting for us, scales up to 50 qubits that we can really play with, and I will afterwards show you results along these lines where we're using these 50 qubits over here. And then there's sort of us as theorists over here, thinking about what to do with all of that. But the great thing in Innsbruck is that we have access very often, like in the Equoquia lab, directly to the machine which is downstairs, so we can program from our desk and sort of like in a kind of a cloud, these machines over here, and do interesting stuff. And just to give you this pictorial view here, this is how this lab looks. I mean, it's like if you have good friends with experimentalists, you get these very nice figures, pictures that you can see over here. And a few years ago, it was 20 ions, in the meantime, 50. And I will tell you afterwards about some of the experiments that are running at the moment based on this theory experiment collaboration that we have with these guys on these 50 ions. So let me now start to talk about physics. So if you have an analog simulator like the one that we have here for the trapped ions, you would say, well, the natural kind of experiments to do would be, let's look at quench dynamics. It's very interesting because you might prepare, for example, initially some product state over here, and while your time involved, this is not one of the IB states, you quench the system over here, and you create a very highly entangled state. It's exciting, of course, that this is an isolated system to a very high degree of freedom. Therefore, this makes it suitable to study quantum many-body physics and entanglement, in particular many-body physics. And this will actually one of the main themes of the talk that I will give now in the following. When the experimentalists do experiments, they have these single-site readouts, so they will, on a certain basis that they choose over here, measure certain probabilities from these bit strings that you can work out, if you do these things many times. Here's some quantum expectation values or correlation functions, whatever you would like to have. But sort of coming to the programmability. I mean, we would like to program these quantum simulators in the sense that you do one problem one day, but maybe a completely different problem the next day. And you don't want to do it by just studying the native Hamiltonian, which is kind of given in this context over here. You like to program. And the obvious kind of gates that you can do is this: that you have maybe this kind of icing interaction over here. You might have single-site addressing and so on. And I guess all of you who have seen these ideas about variational ansatz, for quantum simulation, or maybe in context of quantum chemistry, you sort of realize that we can generate, by going into a certain depth of these circuits, the whole family of entangled states over here that are parameterized how long you leave these interactions on. Clearly, this is not universal what you're doing over here, but it is something that will produce us an interesting class of entangled states. And you might ask, what should we do? Well, first of all, let me mention that the resources for the trapped ions would be the ones over here. We have these, icing interaction that are entangling, but we can also add these local rotations. And these are the ones that basically, build up this gate set that we can play with at this point over here. Well, sort of the obvious thing is that, well, when you are running your circuits that you have constructed over here, and doing the measurement, variational classical quantum algorithms are sort of the very natural framework that one should think about it over here. The obvious thing what to do here is this: to define a certain cost function, and I will give you afterwards actually several examples. One will be the energy, that's the variation of quantum isotope, but afterwards we also talk about atomic clocks, where we specify completely different kind of cost functions that have to do with quantum metrology. But the basic idea is that you generate a certain ansatz over here on your quantum machine, you do the corresponding measurement, and this cost function over here is evaluated then on the classical machine optimizing with a certain number of variation parameters. In practice, you can do about, local optimization with 20 parameters are kind of standard. And then the right-hand side, we assume that this is the part where the advantage comes in of a quantum machine, that this is evaluated efficiently in this context over here. That's sort of what the claim is. And Of course, the example that probably many of you have seen is that you take a certain target Hamiltonian and you would like to find the corresponding ground state. And the interesting part in this whole story is this, that you can specify certain target Hamiltonians, whatever it is. The quantum chemists, of course, have particular experience in that. And then you can generate your ansatz, and then you can see what it really comes down to is this, that you have to evaluate these cost functions that you have on the right-hand side over here, which if you insert this, it simply means that you have to measure the, these first order expectation values, and then these correlation functions plus possibly higher ones over here. So at that point, you would say, well, programmability that you have over here would allow you to optimize now for certain quantum states. And a few years back, and this was sort of the starting point of this whole discussion, and so I just want to mention this as the statement here. This was sort of quantum technology as we had it in 2018. What we did then is that we took models like, say, the Schwinger model of quantum electrodynamics in 1D as a kind of a test case. No, I'm not talking about the physics here. This is electrons coupled to the quantized electromagnetic field, where at the end of the day, you map these things to some spin model that looks really, really ugly. And then you are trying to find the ground state, and then these kind of the energy curves, how you generate with them as a function of these iterations over here, converging down over here, converge to a value. This is the theoretical value here, that's the experimental one, and this is the theoretical first excited state. And we could even, in this case here, measure the corresponding variance of the Hamiltonian, sort of self-verifying that indeed you have produced a ground state, because the error that you measure in the quantum machine was actually smaller than the measured ground state to first excited state distance. Take these things at the moment sort of more as a technological statement, and it's kind of the starting point. At the end, we're going to ask ourselves, can we channelize these things to the many more ions that we have right now in the lab? And let me also emphasize that it was people like, for example, Rick van Bijnen over here, that developed all of the corresponding software where we would, do the optimization on these quantum machines and so on. So this really means there's a lot of technology behind it, but we, at the end, of course, would like to do physics. So, having seen that, now let's move on to more ions, and this is something that's happening actually at the moment in the lab as we speak. First of all, you might ask yourself, what about, can you do it with 31s, or at the end, and even with 51s ion, the same kind of game? And just to give you an example, and this is our preparation for the discussion to follow now afterwards, because this is where the real physics will start. You specify a certain model. I take the Heisenberg model as one example. To do that, you define certain variational quantum circuits over here. The details are not important. Again, you see the trajectories of these energies sort of converging down here, where at the end of the day, you get certain final energies. This is not optimized here at the moment. That's the real ground state. This is what you obtain over here. And you can do even the same thing then for 51 ions, producing approximate ground states. You can see this is pretty hot. We still have to work on these things. But for the starting point for the following discussion, simply take it like this, use specified model, like the Heisenberg model, and we are able to get something which is very close to the ground state. But think of it like kind of a finite temperature state that you have, of the order of a few J's, if J's is like coupling to the Heisenberg Hamiltonian. And I think that's quite amazing, because this means that we can create, for any model that you tell me, if it's reasonable, approximate, not really ground state, but something which is rather close to the ground state. And now at that point, you can start to ask, so what's the new physics that we should now discuss? This is technology so far, this is preparation, but it's now the starting point. And sort of programmability of your quantum simulator, this is what it gives you at the moment. So what are we interested in? Well, actually the most interesting thing about these many-body systems is to study entanglement, either in quench dynamics or maybe in ground state, and you would like to learn more. You would like to learn more about these things, beyond the kind of standard observables that all of us always see in the lab here. So we have here our 50 ions, and we can do either in quench dynamics or to prepare close to the ground states, these 50 ions that we have over here, and now we want to learn that. Let me remind you with a few slides, when we talk about entanglement or bipartite entanglement, what we're really after. When you have a system over here, and I'm drawing it in 2D, like the Rydberg communities, of course, would be able to do that immediately, and I define a certain region A, then I trace out the part B of my, say, ground state wave function of my quench. It defines a reduced density matrix here, And you might sort of take as one measure of entanglement the purity, which is simply trace of rho a squared. This is a number, or we would also call that the second radial entropy over here. So this would be an example that would be a quantifier of entanglement in our system, and we would like to measure it, say in quench dynamics, and see how it goes from a product state to something which is more and more entangled. And the question that you might ask is, how to measure, and that this is not entirely obvious is, of course, well, you might say always, suppose that I do tomography, for my subsystem with that. But if you're doing tomography for the subsystem that you have, it is expensive. It is exponentially expensive with the subsystem size. And you would like to do something or come up with a measurement protocol which is sort of better or easier, scales better with the subsystem size, because you want to go to subsystem sizes that are as large as possible in the context that we have over here. And you can also see the problem over here that these purities that we are talking about over here, they are the square of the density matrix. And of course, observables that we measure traditionally in our experiments, they are not like density matrix squared, they are sort of linear in the density matrix. And so the question also arises, how do I do that? And of course, in tomography would be one answer, not over here. At that point, we can actually start to become a little bit more greedy and ask, well, we were just talking about the purity. What about things like entanglement Hamiltonian, where you would do stuff like, I have my density matrix, I rewrite it in this form e to the minus h tilde a, defining the entanglement Hamiltonian. And there's a lot of physics in finding the eigenvalues over here, this entanglement Hamiltonian that we call the entanglement spectrum, or then really the structure of the entanglement Hamiltonian per se. So can we learn the operator structure of that you will ask, why is it interesting? One example why it's interesting is that, always like this Lee-Haldane example, I will not talk about it afterwards, is that you can find, for example, in this entanglement spectrum, supposed to be able to measure very interesting fingerprints of topological phases, because it's this point-edge correspondence, as we call it, that the entanglement spectrum has a certain structure, and in this structure is sort of encoded, the properties of your topological state that you have. But I will go now in a somewhat different direction and talk about something that I learned actually first from Marcello Del Monte when he was a postdoc in his book, namely the so-called Bissiniano-Wichmann theorem. That's a very mathematical paper, in relativistic quantum field theory, that tells you what the structure of this entanglement Hamiltonian is supposed to be. In relativistic quantum field theory, that's a theorem. In our context that we have over here, because we will work on the lattice, it will be sort of approximate if it applies. And we are going to test it now in the following. This will be one of the test cases that we want to do. Let me tell you first of all what it is, and I find it actually pretty amazing that this is true. Take any relativistic quantum field theory, the assumption Lorentz invariance, and of course it's in the continuum. The statement there is that, that the reduced density matrix that you have over here, when you have, let's think about a 1D system, actually this is valid in all spatial dimensions, and you have a bipartition A to the right, and B then here to the left, that this reduced density matrix, where you traced out the part P that we have over here, can be written as e to the minus, and then it sort of looks like a kind of a dip state, a thermal state. And it has one major difference, and this is the fact you can see that the temperature over here depends on the position. So this means that the temperature gets hotter and hotter and hotter the more closer you go to the cut. So the closer you go to the cut, the more mixed the state is. Intuitively, that's very obvious, right? Because if the system is entangled across the cut, it will be very mixed, just at the point where you got your cut. So if you plot this inverse temperature, it has here the form of a ramp. This is this Bissiniano-Wichmann ramp. And you might ask yourself, can we see something like that? It's a very fundamental statement about ground state, in an experiment. Let me sort of emphasize that it's quite amazing that the entanglement Hamiltonian that we can read off over here is actually just the original Hamiltonian. This is the Hamiltonian density, here multiplied by x. This is this Bissiniano-Wichmann ramp that we have over here. So the entanglement Hamiltonian is nothing else but like the original system Hamiltonian, but you have a deformation of your coupling coefficients. Yeah? So if you got some Hamiltonian and you put the coefficients in there, make them a ramp, and you got the entanglement Hamiltonian. That's sort of the statement behind all of that, what it means. You can do that, by the way, also if you assume a conformal field theory for something which is just some region in here, and then it has the shape of a parabola. Again, high temperature here, lowest temperature in the middle. This would be the critical points, again, with the structure that we have over here. So this is, again, the original Hamiltonian, and you have a parabolic deformation of that gives you the entanglement Hamiltonian. Can we see that? Then let me compare that, with the normal Gibbs state that we have. In the Gibbs state, it will simply be sort of flat temperature over here, because you might have resistance that simply thermalizes to the rest. So this parabola relative to this is the signature, sort of the quantum signature of these entanglements that you have, for example, in the ground state or in the vacuum state of the quantum of the relativistic quantum field theory. You can adapt all of these ideas now also to lattices. In the lattice, you would have now atoms over here, and there's some sort of simple recipe that comes out from the whole story. And this recipe is simply that if I have a certain Hamiltonian, the entanglement Hamiltonian, according to this Indiana-Wichmann, if you believe that it should also work on the lattice, it's just a local deformation where we would like to learn these coefficients GL that we have over here, possibly also have some certain corrections that we have on the right-hand side. And these ideas have been studied, and Marcello and others have written now a review about all of that will, I guess, come out very soon. There's a lot of evidence that these ideas hold, from numerics and so on. In this case here, and also from analytical results.
Sorry if you made this clear earlier, but does this require the interactions to have some locality? Like if I have multiple...
Yes, it is a local quantum field theory.
Okay.
Okay, so you might ask, can we see that? Well, at that point, you might say the following: let's go to the Heisenberg model I talked about before. I just told you, let's pick a Heisenberg model and produce an approximate ground state. This was one of our sort of warm-up exercises that we did on our quantum simulator. And if you do the numerics, you do DMRG for 51 sites, you can find what these GLs are, this deformation. And you can see these very beautiful parabolas that you have over here. So that's sort of a numerical confirmation, you might say, this Indiana-Wichmann. But then you can also go to the experiment. And as you can see in the experiment here, we observe that. Okay? So this is an example. I think it's actually the first experiment ever done demonstrating that this Indiana-Wichmann deformation, in the sense of, and you would expect it only to be great at a critical point, but it's also sort of, valid if you go away from all of that. There's no error bars in these things over here, but this is for 51 ions, and you can take subsystems. We believe that we can go up to something like maybe 25 or so subsystem sizes in doing all of that. It's really sort of discovering new physics and why you have the programmability of the quantum simulator to make your sort of low temperature state in the first place. But then also you go along and then you would like to design, and that's a part that we'd like to talk about now the following. How do we actually get these coefficients that we have over here, these GLs, these deformation, these parabolic ones? How do we extract them from the experimental data in the way that we can do them for subsystem sizes that are then 20 or whatever like that? The moment this is here. And not only that, we sort of learn in this way, of course, also the operator structure, the entanglement Hamiltonian, and it allows us then from an experiment to measure even the whole entanglement spectrum by diagonalizing the Hamiltonian. And we can compare that with exact theory. This is sort of the first try to do that, and the agreement is sort of not so bad, down here. We have to work on that, okay? But you can see that there's one point which is sort of left over, and this is what I would like to spend really some more time in my talk, and it's very important. I told you at the beginning what to do is our programmable quantum simulator produces us an approximate ground state. I have not talked about the part yet, how we fit the experimental data that we get, that we can read out, maybe again using the programmability that we have in our simulator, in order to get, for example, these deformation coefficients GL that we just talked about. Okay, how do we do that? And I think that this is sort of important and very central. We talked so far about sort of, under quote, programming interesting quantum states. You give us a Hamiltonian, and we know how to run some low depth or deep depth circuits, producing an approximate ground state. But now we want to talk over to how to sort of program here new measurement paradigms. And this, of course, leads over to these ideas that Andreas Helm, that was working on these things in Innsbruck here, together with Variational, which is very much related to the classical shadows. We called it Randomized Measurement Toolbox. And we started these things a few years ago. And of course, independent here, these classical shadows coming much more from the quantum information side, were invented. And on the Innsbruck side, it's really Andreas and also Benoit is now in Professor Grenoble, and the guys down here, they are the ones that are responsible for these results that I showed you earlier, that have actually used some of these things for producing this Bisonana-Wichmann demonstration. We're writing at the moment with John together just a little nature review over here. And there's one important statement that I guess John invented. It's called, measure first and ask questions later. This is what's behind it. I always think of it, measure first and think later. Okay, maybe that's very similar. Let me make two remarks. So historically, when we first thought about this, when Andreas participated in this experiment and actually invented some of these schemes here, this was a theory experimental paper that produced a data set. And this data set, at that point, we were just after the Rayleigh entropies. We could measure Rayleigh entropies. But actually, it turned out that this data set was kind of a gold mine. That a few months later, we found out, we can also measure this and this and these things that we never dreamed about. So this idea of sort of measure first and ask questions later, I think that's very fundamental. You did an experiment. You stored classical data for this experiment, and then you can analyze it, asking completely different questions much later on. Okay. And that's very important, And what I really appreciate in these classical shadows is that Robert, Richard, and also John, came up with rigorous error bounds. They are the ones that really quantified what we also should have done, but we were sort of more numerically oriented. How many independent randomized measurements does it take in order to, and then you specify certain error bounds. So they made it quantitative, and that's very important. This is now sort of the rigorous, quantum information result of it. So that's very exciting, but let me sort of now tell you a little bit, first of all, the history of that, and show you some results, in particular about this golden data set, and then come back to the question, we wanted to show how to get this out of our data. And this will basically answer that. So again, we have here some state preparation, entangled state, ground state, or whatever quench dynamics that you do. Again, we do our measurements. But what you do with these randomized measurements is that you take the beautiful wave function over here, but then you mess it up by, for example, either a global or a local, random unitary that you apply to the whole thing, which means that the probabilities that you measure will depend, of course, on the unitary that you use to scramble up this whole thing. And but the basic idea is not that you want to look at the expectation values or correlation functions or underlying now this probability distribution. The basic idea is that you would like to look at cross correlations between either a self-correlation, the probability with itself. You can see that this bar over here is the one sort of averaging over the noise, so these random unitaries. You can also see that this is an experiment you can do on day 1, this is day 2, so this you can compare sort of quantum data at different times. And also in different labs over here. These are the kind of experiments that you can do here. Let me give you a particular example, because this was sort of the historical one, also producing the data set that I talked about. When you want to measure the Rayleigh entropy, you can see that will be a random variable here, depending on this circular ensemble unitary. It depends on these probabilities, and if you take the average of this random number, the claim, I'm not going to prove it over here, is this, that this is the Rayleigh entropy over here. At that point, you will ask a lot of questions. How many measurements and unitaries will it take, and what sort of optimal, and how is the scaling of the error, and so on. Then we come back to this thing a little bit later in a somewhat different context, but I will be actually very brief about that. Let me rather show you the results. Okay, this is sort of the experimental result that produced this magic data set that afterwards was recycled according to this measure first and ask questions later. What the experimentalists do, I said before, they have trapped ion simulators, and they realize a model like the one over here, they operate in this regime, but it's like an XY model with a transverse field. They can even add some local disorder to the potential if they want to. And the data, this is the ions over here. You can now start to measure purities. So you can measure purities. In this case, that's the example for 10 ions here. You can do it for the whole system, which would be over here. This is here the purity for the total system of the 10 ions. And if we start out with a product, say it's supposed to be 1, you can see it's not, and this is sort of, an indication that we have some measurement errors over here. So this is the, purity of 1 qubit or 1 spin. This is the data for 2 spins, sort of the first and the second, and then the third. So you walk over. So this is the total system over here, and this is only 1, 2, and so on, the reduced density matrices. And if you look at quench dynamics in this case over here, what you will find is this, that it's sort of, propagating like that. And you can also compare that with theory. You can see that the total system wave function, remains as pure as it was at the beginning. But the fact that this thing sort of goes down over here, it's much more mixed over here. This is an indication that during the time propagation, the wave function gets highly entangled. Okay, so if you cut the wave function in 2 parts, each of the parts is actually very mixed, indicating the entanglement, while of course the total wave function will stay pure, and this is then the corresponding ring entropy. We can see the total state is approximately stay pure, while of course it has this kind of a bell shape that you see in many of these numerical calculations that people have done. I think it was the first observation of this type, really in this form, and sort of to jump now more recently, where you just take a data set over here. Again, Andreas was fundamentally involved, and we wrote this paper that included now essentially everybody. Also, John is over here, and Richard is here, and Robert, and so on. Now, when we looked at the corresponding transpose, and there was a certain criterion for entanglement, mixed state entanglement. I think that I'm not going to explain the details to you. It simply means that all data are recycled. You had them on your classical hard disk of your experiments. You could reanalyze them according to the new insights that you had to get completely new things out of. Like finding here, entanglement criteria for this partial transpose. Let me now sort of go back to the quench dynamics, and you might ask, I said before we start out with the product state, but in the course of time evolution, things get sort of entangled, until of course we would expect for very long times things actually thermalize. Can we actually see the build-up of entanglement in quench dynamics? Really sort of see the Schmidt decomposition live happening in an experiment from a product state all the way to an entangled state. And to remind you, the Schmidt decomposition is what I'm writing over here. The wave function is a superposition. If I make a bipartition between the part A and the part B, it is sort of a superposition of an A and a B part. And then we have a certain number of Schmidt values here in front. And this psi alpha that I'm writing here, this would be the entanglement spectrum. So we would like to see how the state gets entangled, and we want to observe it sort of while the whole quench is kind of propagating. And well, again, there's a formula, and I have to afterwards tell you a little bit more how we fit, data that we can take over here. This is sort of randomized tomography to extract the entanglement formula. And here is the maybe a little bit slightly more technical slide, but let me just tell you what the idea is. You took some data. This is our gold data set that was taken years ago, where we had no idea of all of that. And then you design an ansatz. In the case of quench dynamics, this is not so obvious. I told you before, this is Jan Wichmann. Conformal field theory gives you ideas, but it could also be here, but let's not talk about these details here. And then you can do this kind of a fitting that I will explain now, right? You fit to the data, and then it takes more data to verify. If you would like to see the whole beauty of the whole algorithm, this is, you do the measurements, you make a certain ansatz, then you fit, this would be sort of in John's language, these classical shadows that you have over here, to the ansatz that you have here, and then you would like to find out that this makes the whole thing sort of efficient, that these number of coupling constants over here, they are a very small number. They scale with the system size and not exponentially like in the Hilbert space case. And then we can verify by looking at the overlap, and we have again protocols for doing that. So I'm a little bit brief here because it's technical, but let's look at the result. I mean, this is where the interesting physics starts. Data, and design ansatz, construct. If you do theory for the quench dynamics and you ask, what are the Schmidt values? It's a function of time. You will see that at the very beginning, 1 is 1, all of the other ones are 0. And here you can see that while the quench is sort of progressing here, more and more of these values coming in until at the very end, at one point, the whole thing will actually be thermalized. If I take a subsystem out, then it would be a big state over here. So if you take experimental data, you can see them over here. They fit the theory really, really nicely. I mean, this is sort of observing here this build-up of entanglement with the Schmidt values. Quite amazingly, if I take all of the measurement data, that we have stored here classically, and you only take 1/100 of these data, I still get pretty good results, here. Just the error bar gets a little bit bigger. So the amount of data that you need in order to get that is actually remarkably small. And we can then also work out the entanglement spectrum over here at a certain time, and also work out things like von Neumann entropy, how they increase. This is the von Neumann entropy of the subpropagation increasing during the French here. And the same we can also do that for a much bigger system. So at that point, I've sort of given you the idea what we did in order to extract the Bissiniano-Wichmann thing. We have Bissiniano-Wichmann, we had an ansatz, and this ansatz was an efficient ansatz that it only depended on a very few number of parameters, and you could fit this thing to data where tomography would fail completely, but in our case over here, it is sufficient to reconstruct this thing here. And just to sort of show you, and this is examples what you can do in the theory side. In the theory side, you can simulate experiments, without any noise. I mean, that's the advantage of theorists. But and if I take one example over here, you can see that we have here transverse easy model, exactly what the ions do. This experiment has not been done yet. There's a phase transition over here, and we get the entanglement spectrum, with a relatively small number of measurements, exactly what's typically done in an experiment, very, very accurately. But sort of more interesting is that you can see here the Bissiniano-Wichmann ramp. But the reason for showing you this figure is how many measurements do we need with our way of sort of fitting or sort of this efficient tomography, having an idea of what the entanglement Hamiltonian is. And you can see that for certain subsystem sizes, if you require that the fidelity of reconstructing this reduced density matrix is larger than 98%, that's a big number. Tomography over here would require 10 to the 8, or maybe another form of tomography, 10 to the 6 measurements. We get away for system sizes that in this case go up to 17 or something like this, with about, say, 1,000 or maybe 10,000 measurements. So this thing is really efficient. We can go to large system sizes, and that's sort of one of the key killer applications or features of what we have over here.
Can I ask you about that? What's the difference though of what you did here compared to the local randomized measurements? So why is this more efficient than the? I mean, it's more efficient than the local randomizing.
Well, this is more efficient than the. This is tomography over here.
Yeah.
Okay, this is low-rank tomography. You assume that the geodensity matrix is basically just the rank 2. Still, it is exponential, and in our case, because of the efficient answers, we are down here in much less.
Maybe my question is that still done via local random unitaries?
Yes, that's
It's just a different way of evaluating.
Okay, so let me spend now a little bit more time on sort of really changing topics. I mean, I talked about programming quantum simulators, and I gave you sort of 2 examples. I said, let's prepare states, and let's design and sort of kind of measurement protocols. What we can do with these states to infer maybe new things, like seeing for the first time the Bissiniano-Wichmann theorem, or sort of very fundamental predictions that we have in this case. Let me now switch over and simply say, is this idea of the programmable quantum simulator, can we also run it as a quantum sensor? Can we do now metrology? Should we sort of maybe can we build a better atomic clock by designing now variational algorithms very much along the lines that I talked before, in the context of preparing ground states, like the variational quantum Solver. But now, in order to find, for example, the right entanglement that we need to operate, say, an interferometer, like the Randomized interferometer, which you need for an atomic clock, in an optimal way. And I would like to tell you a short story that, again, sort of follows the same paradigm I said before. You have a theoretical idea, you try it out, you work it out theoretically. At the end, you go to the experimentalist and ask him, okay, you want to try that? And it works, okay? And in that point, maybe there's not so much market for selling entanglement spectra, but I guess there's a market for atomic clocks. So what I want to say is this: we are actually doing something useful over here, that maybe even has some real-life impact. Maybe that's the reason why some of you are interested in doing quantum physics at the end of become quantum engineers. So that's a theory paper, and Raphael Kaltbecker, Denise Vasiliev is over here, and then we have Christian Marciniak, who was sort of the lead on the experimental side. I have to confess here that this experiment did not run on the quantum simulator because they were busy with other things. We would like to do that with 50 ions, so we had to, as a second choice, but actually it was a very good choice. Go over to the quantum computer, produced, run by Thomas Mons. The quantum computer is in a rack over here. This is one of these things that Thomas leads in his company. You can buy, maybe you get it as a Christmas gift from your parents. So it was run on the quantum computer, but really the mode is like a quantum simulator mode. So that's not distinguishable. Let me tell you what the basic idea are, what we are trying to do. I guess all of you know interferometry, Ram's interferometry. What you do in Ram's interferometry is that you have, say, n atoms over here, and these are two-level atoms, and they can be spin up and spin down. And the Ram's interferometer works like this: that you apply pi over 2 pi's, that makes a superposition of up and down, and then you imprint a phase on your interferometer. This is a certain phase phi that you have over here, and this is the phase that you want to measure. So we want to do parameter estimation. Standard thing is to do all interferometers actually do. And at the end, of course, you measure here the interference fringes. This is the standard interferometer, how everybody uses it out there, in different contexts, just written here in the context of atomic Ram's interferometer. The question that I'm going to ask now is this: entanglement, we know, is good for quantum sensing and for interferometry. Imagine now that what we would like to do is we insert at the very beginning, instead of the pi over 2 pulses that act on the individual atoms. What we had in the first slide was product states. This defines the so-called standard quantum limit. Let's put in entanglement. Okay, the most general entanglement I can always write as a U, and I call it En for entangler. I put an entangler here, acting on the n atoms, so you can ask, what's the best entanglement? And at the end, this will be done variationally. You can see some parameters over here. We're going to specify resources for doing that. And very similar, I mean, I have an entangler over here. There's also a decoder here. You want to do an entanglement measurement. So you have two unitaries over here. And then you can say, what's the best possible interferometer that I can build, given certain resources that build, for example, up my variation quantum circuits. In other words, we are now up to defining or identifying a cost function for metrology. And, when I ask you, okay, so you would like to do a Ramsey experiment, and imagine our virtual discussion with an experimentalist. You say that, you would like to do a Ramsey experiment. What do you care about? And then the experimentalist might tell you things like, well, I really care about signal to noise. Can I go beyond the standard quantum limit by having some entanglement? And I would like to get the best possible out of our words. But at the same time, I also have some limited resources because I might not do a very complicated data set that you're asking me for, but I can only do certain kind of operations. These certain kind of operations, for me, define the resources that go into the circuits that I can try. And then I don't optimize for the over everything, but maybe only over a subset. And you might ask yourself, how close do I get to the optimal interferometer? With something which is only maybe limited resources. But in defining this cost function, the signal to noise ratio is sort of one thing. But there may be other things, like on the wish list, this is the wish list that defines that. These are the resources that you put in over here. Let's think about what people building an atomic clock would actually care about in the case over here. What they would care about is as follows. Well, how does an atomic clock work? You got some light over here. This light, is your oscillator. These are the ticks of your clock that you have. And of course, clocks have classical noise. They will diffuse away. So this phase will sort of wander off. This is drawing it over here as a function of time. Initially the phase is 0, and then it's sort of, think of like a phase diffusion walking away. And the longer the time that you take over here, this distribution gets broader and broader and broader. What you would like to do in an atomic clock is that number one, you would like to take this time here as long as possible. We talk about the Ramsey in a moment. But you don't want these bits over here, to be sort of overlapping maybe with the next interval, so that you get something like a fringe hop. You don't want this to happen. So an atomic clock circuit works like this, that you want to take this lace over here, and then you would like to lock over here. This is what you do with the Ramsey experiment. You would like to find out what this phase is that was accumulated over here, this broad range of the width that's given by this delta phi, and then you want to lock it to an atomic ensemble via this Ramsey experiment. So when I said now that, what's my methodological cost function, well, similar to noise like before, but I want, that the sensitivity of this thing is as broad as possible over a very broad range. This is what atomic clocks want. It's not like in LIGO. In LIGO, you only have very small phases you want to measure. Here, I really want I want optimal sensitivity as low as I can get in terms of signal to noise, or noise to signal, as broad as possible. And you write all of these things that you want as the wish list in your cost function. Okay? And then what you do is this, that you have defined a methodological cost function that has two powers. There's one entangler. There's a second one, which is now one, which is simply a decoder that has the collective measurement. In this pair of unitaries, you want to optimize it according to the criterion that the instrumentalist specified to you. And we can try to play this game and sort of, what you do over here is this, that you have the prior knowledge over here. You can formulate this as a Bayesian approach, that you have here an initial distribution. And what you would like to learn with your measurement is that you would like to learn as much as you can about what the phase actually was, and sort of after the measurement, the value would be delta phi. You would like to maximize the knowledge that you have after one measurement, delta phi. And this is what you identify as the cost function over here, given a certain delta phi that you have. We can formulate all of these things into a cost function and run of all of that. Let me show you what the results are. Okay, so cutting a long story now short. When I go to my colleagues in the lab, and they're doing a Ramsey interferometer, this would be product state over here. Interference fringes, you can see this is the product state, this is the interference fringes, that you can see over here, and this is the mean square error, this is the noise. It has sort of, it's roughly over here, this defines roughly the standard quantum limit over here for a particular delta phi that was specified over here. So this is the standard Ramsey interferometer for product states, standard quantum limit. Some of you might say, well, let's add squeezing. Okay, so let's add squeezing to this story. You can see that squeezing, this is a squeeze at the very beginning. There's a certain circuit over here. It doesn't change this interference curve, but you can see that in terms of noise, we go lower. This is what squeezing does. I mean, all of us know squeezing, interferometer, also LIGO does that, and so on. But here we talk about this thing in the context of atoms. But now we can sort of, this is what we call one encoding layer. So we call this thing 1,0 because we put one encoding layer over here, and we have a certain circuit over here that I'm not going to explain. What we could also do is this, that, well, we don't entangle at the beginning, but we try to do entangled measurements back over here. But now you can see what happens here. This curve over here got much broader. So over here, with these decoding circuits, what we did is that we increased the dynamic range of the interferometer, really what we wanted to do in the first place. And you can also see that in the noise down here. This is sort of flat, but it is much broader than what we had before. This is what I was asking for in this decoder tool. And now you can really go for the whole thing, sort of, encoder, decoder, 1,2. We have one squeeze in front and then two decoders over here. Now you can see that we are broad and we are deep. Okay? And the amazing thing is that this story over here, this interferometer that we built, when we let the machine and at the end you can find its own optimal working point, that this is sort of, maybe I don't explain this and then in too much detail over here. This is sort of this prior knowledge, posterior knowledge, in the Bayesian update. I'll give a talk tomorrow for the students and I will explain this in much more detail. This is sort of this ratio of this update delta phi, the posterior value, the prior value over here. And we are actually very close here to the optimal interferometer. So the optimal would be the red, this dashed line down here. This is the classical one, standard quantum noise limit. And we go far below the squeezing and with the low depth circuit sort of approach almost optimality. I think it's kind of good news. This is a useful problem. It is something that's sort of easy to do in an experiment, because you only need low depth circuits, but you already go close to the optimal quantum interferometry. So that's, in my opinion, a very nice example of designing now variationally quantum processes to do something useful like interferometry in order to achieve that. And here's sort of the last slide in this context. Well, the data that I've shown you so far, were sort of the key theorists do our little calculation, come up with parameters, we hand them over to the experimentalists, and then they punch these things in and then they run it. But imagine that you don't trust theorists. I mean, this seems to be the rule, I guess. Okay, whatever. So if you don't trust the theorists, or you don't trust the machine, because your machine maybe has certain imperfections, maybe you would like to run this optimization circuit directly on your machine. So let the machine measure the cost function, and then you let the machine, by these optimization algorithms that I told you about earlier, find out what the best operating point is in the presence of imperfections. And so the same, global optimizer, like Rick van Bijnen, that I mentioned before, can also be applied over here. It has to be a little bit adapted. And you can see now, before we talk about energy going down, but now we talk about this variance. This is our cost function now going down over here. And you can see how it sort of converges and agrees actually pretty well with the expected theory result. This machine now really finds its own optimal operating point. This is the standard quantum limit. This would be squeezing. We go really far below, and this would be the optimal interferometer down here that we do not reach with a finite depth circuit over here. Okay. So in this sense, you should see that like that this atomic clock is kind of booting up, finding its best operating point, giving the decoherence that it has, so the imperfections. And actually, in the experiment, this was very fundamental. When I talk to the experimentalists and they want to calibrate their quantum computers, the say Mölmer-Sørensen-Gate, when they want to calibrate for 26 ions, they have great difficulty doing so. The reason is that at that point all of the curves are flat, and calibrating is very, very hard. But nonetheless, the variational algorithm, I mean, you don't have to calibrate these things. You just have to look for the optimal. Okay, so in this sense, you can run this optimization algorithm in the regime where the calibration of the machine fails, and also in the presence of sort of decoherence, and all of that. So it finds. I mean, there was no surprises here because our theory got the right point, and the experiment was actually pretty well calibrated anyway. But it was nice to see in running this sort of optimizer on the quantum device itself. It improved a little bit, but not very much, okay, because it was sort of good in the first place. Okay, so this sort of concludes now my story, and you can see that I was sort of, talking about various things. We prepare interesting quantum states, prepare, device and protocols that we can program to get completely new quantities out, like demonstrating for the first time Pizziniano-Wichmann in an experiment, very fundamental properties of entanglement. But at the end, the same ideas are also useful for optimizing quantum processes, like an interferometer, and we let the machine find out itself, given the resources, which is specified as the depth of the circuits and what kind of entanglement you put in there, what sort of works best. And I find it very fascinating because it really means that we are at the point now where these machines that people like myself and Ignacio Sirac and many of us here also were involved sort of dreaming up 25 years ago, they are now coming back to us and they are really providing for us a playground where we can do pretty interesting things on the fundamental side, like entanglement, or then on the practical side, like atomic clocks, for example, just to give you one example. So in this sense, let me summarize here. I talked about programmable quantum simulators, various algorithms over here that are always sort of hybrid classical quantum that are somehow matched to that. And then this was this randomized measurement toolbox that this really overlaps with the shadows ideas developed here. The programmable quantum sensors, and this was the Pizziniano-Wichmann, measured. You can see that the error bars are missing here. We don't have the error bars yet. This will come. We are finished with these things here. Or entanglement, build up that you can see in quench dynamics. From the product state, you evolve to something which is at the end maybe something like an almost thermal state, even though you should be careful because there's decoherence and so that's more complicated. Or then, if you put on your head as somebody who is really useful, you do the optimal Ram's interferometry, and you let the machine find its optimal sweet spot in terms of the entanglement that it can create with the low-depth circuit. And with this, I want to conclude here and really mention that Christian Kochael and Rick van Meinen, they are the two guys behind these Bissiniano-Wichmann results that are going on at the moment as we speak. This is done together on the experimental side with Manoj Joshi here. Thorsten Zacher and Daniel Gonzalez, they do lattice gauge theories. This is a theory project at the moment. I've talked about it. Lata does also randomized measurement in collaboration with Andreas and Raphael Kautrücker and Denise Vasiliev. They are behind the RAMS interferometer, and a few more things that we don't really have time to talk about. And this is some former members, prominent one here, like Andreas Elm. And of course, Marcello was very fundamental in defining many of these original ideas. And of course, special thanks go to my experimental friends, that provide these labs. I can tell you they're not always very easy to convince when it comes to doing experiments. They really want to know why it's interesting and why not, and can we do that, and so on. But we found them really fantastic partners in doing these things. And this is the younger generation. Christine Meyer was involved in this original Nature paper on the Schlinger model, and Manoj is now with the 50 eyes, the main part, and Christian Marciniak was the experimentalist behind the Ramsey interferometer that I showed you. And with this, I would like to thank you for your attention.
All right, we're following the scheme of giving talk first, answering questions later. I'm going, if anybody in the Zoom audience wants to ask a question, I'll try to watch the chat, but for our in-person audience. Questions for Peter? Let me start it off. So it's very cool that with a relatively low depth encoding and decoding circuit, you can get this near optimal interferometer. What are the practical applications of that? Do you see, what do you want to measure that'll take you beyond the state of the art?
Well, the idea is really that, the basic idea in doing this better interferometer is to use it in an atomic clock.
Yeah.
And I would say that, of course, people like Junier, they got these amazing atomic clocks at the moment that are unentangled. Of course, they're also working on squeezing. You can either go to larger and larger atom numbers, but you can talk about ion clocks, for example. And ion clocks are definitely a competitor that has maybe tens or maybe even 100 ions or something like this in the string. These ideas will work in this particular context. And then if you are constrained in terms of the number of atoms that you have for running an atomic clock, then this entanglement will help.
Right, so it's great that it's an ion trap, so you can do this. Not so clear you could do something similar for an optical lattice.
Oh, okay. I think that you can do it in the following sense that Junier at the moment, in terms of either cavities or there's also an optical lattice interaction, the ingredients that we used over here that we defined was simply a squeezing operation as it is used standard. So it's a JC square collective angular momentum. And this is available on many different platforms. Okay? So this is available. But actually, the really interesting part, this is sort of maybe what you're thinking about at the moment. When I think of what, for example, Manuel has, here's the 2D array, and here's a finite range Rydberg interaction. If you ask us to come up, if this is a quantum resource, then I would like to optimize. Classically, my classical computer, in contrast to what we over here, I'm dead in actually predicting what the optimal values are. Because you have to solve a quantum many-body problem. Here, in the case that we have here, we always have a symmetric subspace. It's not a complete Newton space. It turns out it's just in the linear subspace. Therefore, we can do calculations up to a few thousand atoms very easily. But if Manuel, if Manuel has here, Rydberg resources with a finite range interaction, I have to solve a many-body problem in 2D, which I cannot. But he could run his machine, to produce these data. So he could do the optimization one that we talked about here before, these kind of plots that we have over here. for the n atoms that you have, a problem that we cannot solve classically. And I think at that point we're solving a many-body problem or many-body dynamics with a certain purpose that otherwise I would not know how to do.
Is there understanding or intuition to be gained by looking at the type of entanglement or the structure of entanglement that's generated in these optimized encoders?
Yes, I will give a student seminar tomorrow and I will talk about that.
I have a related question. Why does the decoding help when there's no encoding?
Okay, again, my answer is okay, so tomorrow I will show you plots, plots here, plots, you know, it represent linear functions, and they give you a pretty good intuition of what's going on there. So at that point, I think this is probably the best explanation.
So you talked about preparing ground states in the lab. Is there a fundamental limit, and I guess the temperature of the lab is so it was slightly above the ground state? And can you reach that limit, the theoretical limit?
Okay, so the theoretical limit you're simply asking, can I really for 50 ions prepare the ground state? And my answer would be, I guess not. Okay. So at the moment, what we did was we simply took some low depth circuits and we ran it, and it produced some finite energy. Our main emphasis was really that this Wichmann physics that I talked about, you see this parabolic shape and all of that. This is really more a low temperature property, even though formally it is always devised as a property of the ground state. So this is visible, even for low temperature. You can actually see that very clearly in the experiment in the following sense. That I showed you a parabola, but I didn't really discuss the corresponding scale. And it turns out, if you do this thing for a finite temperature, our state is not really finite temperature. Think about it this way, we get an approximate. The whole thing is actually reduced in scale. And so we are sort of getting more thermal. We are mixing a thermal component to the whole thing, and this is very clearly visible. There's no theory for these things out there. Of course, we can do numerics and compare all of that, and it seems to explain all of that. But for 50 ions, really go to the ground state of the Heisenberg model. This would be a significant effort, but I say to this for what you want to do, we actually don't really need that, and that's very good to know, because then you don't have to work so hard.
So where do we go from here, Peter? Where do you see great potential for advancing our understanding of many-body physics, say, in the relatively near term with these programmable simulators?
So I'm very excited, of course, with Manuel has again, that these guys have 2D arrays. And I would say that a lot of the real physics will happen in 2D arrays. These 1D strings are very nice. Ions are fantastic how you control them, but we don't have 2D systems over here. In 2D, I see a lot of interesting things. I would like to see the area law and all of this kind of stuff coming out there. And of course, on the other hand, we have developed many of these ideas also in the context of thinking about Hubbard models. Also in the context of topology. If you talk about topology, you need a 2D system, like for the synthetic gauge fields. Many of the ideas that we have over here can then be used for that. And as I said at the beginning, I really would like to see the Lee-Hardane conjecture being seen in the lab. We believe it theoretically, of course, but I would like to see that. And I think we're sort of almost there to have the tools available for that. But sort of a little bit in longer term, I would say that we're building out programmable quantum simulators, and there are sort of two things we always care about. Maybe three. One is scalability. And these quantum simulators, they go a long way, scalable, but you pay the price of less programmable. At the very end, there will be kind of a crossover to the real quantum computer. But the quantum computers we build at the moment, they are essentially analog circuits. Exactly the devices that we were talking about. These are analog circuits that we are then sort of chaining together. And we are sort of making compromises that will allow us to go to large particle number, because the scalability frontier is, I think, important. But at the end, all of these things will sort of merge into one big thing. Of course, once error correction comes, then, okay, I wish everybody good luck.
Well, that might take a while. But in the meantime, there's a lot of interesting things we'll be able to do.
That's right. And it's fundamental physics that you're doing here, but also I think that the application part we should not completely leave out. It's sometimes good to be useful, but we don't always want to be useful.
Well, I'm happy to go along with that. And so on that note, don't try to be too useful, all of you. And let's thank Peter again.